In this session, we're going to see what Pascal's triangle is. You'll notice there was no PDF for this. We don't have any examples associated with this in particular. We're just going to kind of learn about this entity, so we'll just call it an informational thing. But it would be probably a good idea to take notes, so if you need to, pause this video and get out a sheet of paper. Pascal's triangle is a triangle that has rows and entries. The first number at the top of the triangle is a 1. And then we have another row that consists of 1 and 1. And then it starts to get a little bit more interesting. We have a row that consists of 1, 2, and 1. And then the next row is 1, 3, 3, 1. And it could be really boring if I read the whole thing out, but let's just start to talk about how we would get entries now. For the next row, all rows start with the number 1 and they end with the number 1. And then entries are obtained by adding 2 entries from above. So for the fourth row, we're going to add 1 and 3, and we're going to get 4. And then we're going to add 3 and 3 from the third row, and I'll explain why it's the third row in a minute, to get 6. And then we're going to add 3 and 1 to get, again, 4. And then the row ends with 1. So the fourth row is 1, 4, 6, 4, 1. Again, I'll explain why it's the fourth row in just a minute. And then the next row is going to be 1. And then we add 1 and 4 to get 5. 4 and 6 to get 10. And then 4 and 6 again to get another 10. And then 4 and 1 to get 5. And then 1. And so what do you think the next row is? It starts with 1 and then 6 and then 15 and then 20 and then 15 and then 6 and then 1. So there's some symmetry in the triangle. As far as the counting, the first row is actually called row 0. And then the second row is row number 1. What you would call the third row is row 2. And so it's actually the case that in rows that have more than one entry, the second entry in the row tells you what row it is. So the 1, 3, 3, 1 is, of course, row 3. So it's kind of a weird thing they do, but the thing is they just start counting at 0. That's all. We also start counting at 0 when we refer to the entries themselves. So if we look at the last row that we wrote, which is the sixth row, 1, 6, 15, 20, 15, 6, 1, the first number, the 1, it's entry 0. The 6 is entry number 1. The 15 is entry number 2. And so if we just keep numbering these, we have entry 3, 4, 5, and then 6. And so while there are actually 7 numbers in the 6th row, they are numbered 0 through 6. Okay, I know it's weird. You kind of deal with it, right? And these actually have representations in the context of combinations of all things, believe it or not. And to explain that, what I'll do is I'll single out row 3. Row 3 is 1, 3, 3, 1. And it can be expressed using 3 choose 0, or a combination of 3 things taken 0 at a time. 3 choose 1, 3 choose 2, and then 3 choose 3. And so it's actually the case that for any entry in any row, let me clear and make some room here, the number on top indicates what row you're in, and the number on bottom of this combination notation with the parentheses and no fraction bar, the number on bottom tells you which entry you're in that row. And so in terms of combinations, the 7th row would be 7 choose 0, 7 choose 1, 7 choose 2, and so on, all the way up to 7 choose 7. And if we just pick, say, a couple of these to look at, let's say 7 choose 4. 7 choose 4, according to my calculator, well, forget the calculator. it's 7 times 6 times 5 times 4 factorial divided by 4 factorial times 3 factorial, if you remember the formula for combinations. And so the 4 factorials divide out. 3 factorial is actually 6. 7 times 5 turns out to be 35. And that's the sum of the 20 and the 15 from the row above. That's kind of an amazing fact. I don't know. If you have no interest in that at all, then shame on you and develop it. I guess we can close up this video by saying that in general, entries in Pascal's triangle are of the form n choose, let's say I, where n is the row and I is the entry in that row, starting the counting at 0. Okay, and then, the fact that we have like 7 choose 0, which according to the formula of a combination would be 7 factorial divided by 7 factorial times 0 factorial. This 0 factorial in the denominator is maybe one of the reasons that the definition of 0 factorial is equal to 1. It's just so we don't end up dividing by 0 and that this kind of numbering will work. But this is the story of Pascal's triangle. Actually, it's really not. The story of Pascal's triangle is much, much longer and much more interesting. But for the scope of our purposes, we're going to leave it at that.